Okay, we are going to continue our conversation on vectors. Okay, we on Monday talked about the basics of vectors, unit vectors, direction, magnitude, all of that fun stuff. Yesterday, we added in basically how we work backwards with our components. Now, today, we're actually going to start using them to do some more things. So, most of our focus today is going to be about the dot product, what it is, what it can help us find, and then we're eventually going to see how we calculate work using vector forces. Okay? So those of you who are in or have taken physics, it'll be somewhat of a flashback, but we'll have to talk about some units and stuff when we get there. But today is pretty much all about the dot product. So what is the dot product? Okay. First of all, write down that vector u is u1, u2, and vector v is v1, v2. Okay. Or u sub 1, v sub 1, all those subscripts. Okay. There are actually two different ways to multiply vectors. However, the second way you can only do if you have three-dimensional vectors, and we're not going to mess with that. Okay? So this is the only way you are going to learn how to multiply vectors because we're limited to just the two-dimensional plane. So there's two different ways to notate multiplication. Sometimes we use a dot. Sometimes we use like that cross like we did way back in elementary school. Okay? Like 1 times 2. Yeah. You never use that to notate multiplication?
Oh,
yeah.
I did.
An X. Okay. Sorry. An X. Okay. Since it is the dot product, we're going to use a dot to notate our multiplication. Okay? So this is how the dot product works. We are going to take the horizontal components and multiply them together. Then we'll take the vertical components and multiply them together. And with those two products, we will add them. What is our answer going to look like?
It's going to be square.
Not necessarily.
But it
Is it going to be a vector?
No.
It's going to be a number.
Oh, what?
We call that a scalar. When we multiply vectors using the dot product, our answer is a scalar. Go ahead and write down vector v and vector w, and we will together find their dot product.
I and I are on the same
Depends which font you have, right?
Unfortunately,
I guess so.
depends on the person.
Mine's is best.
Really, Emily? Isn't it weird how, like, World Wide Web is shorter than saying www?
Yes.
I propose to be important.
Okay, so our dot product.
Whoa.
FYI, I'm recording this lesson.
Oh, you are?
It didn't work during first hour, so I am legitimately recording it. Okay? V dot W. Our horizontal components are -2 and 4. So we're going to multiply -2 and 4. Plus, we're going to multiply our vertical components, 5 and 1. So what's our dot product? Okay, that is the foundation for the rest of our work today. Right? I know. Okay, so how about I give you 2 vectors, and at your pod, find the dot product and check it with each other.
You just died.
Find the dot product. 1, 2, 3, go.
No, he just died.
Check with your neighbor. Yeah.
You keep the dot between like the products, like U and V, and like you know, you have to keep the dot there, or you just sort of like U
The dot is important. Okay. Kaylin asked a good question. This dot is important. You need to keep it there. Okay. Josie, what'd you get for your dot product?
-2.
-2. Do you agree with Josie with -2?
Oh, this
Yes.
He said,
yeah.
Does anyone say no?
No.
Graham, do you agree?
No.
Okay.
No, yes.
Okay.
No. No, yes, yeah. Yeah, no. Yeah. I think I'm, yeah, maybe.
Okay. I really need you guys to focus a little bit better. Okay? You don't have to write these down, but you can. They're not going to take us very long, so it wouldn't hurt to write them down. But I want you to understand that the dot product is commutative. U dot V is the same as V dot U. Okay, we're just multiplying components and then adding those products. So the order of the 2 vectors will not matter. If we take the dot product of a vector and the 0 vector, we get 0. Okay, makes sense, right? Okay. Multiplication, we can distribute into an addition problem, right? Well, since the dot product is a form of multiplication, it can be distributed to a sum or a difference. Now, what about if we have if V is V1, V2, what happened? I really hope that.
Sorry, I cannot. I hope they can see it on the computer.
Put it down and pick it up.
Like 5 minutes from now, we'll just stop. Yes.
Well, look at that. Okay.
Are you gonna crop that out?
Okay, what would happen? Don't write this down yet. What would happen if we took V dot V? Well, what do we do with the dot product? We take the component times component, and component times component. Have you seen anywhere where we have horizontal component squared plus vertical component squared? Oh, that's what's under the radical and the magnitude, right?
Yeah.
Okay, so the dot product of V and V is the same thing as magnitude squared. If I asked you to give me this value, what would it be? 24, because we multiply two numbers together and then take that product times the other one, right? So if we have a dot product and a scalar that's multiplied to it, this is multiplication. We don't distribute through multiplication, do we? So if we have a scalar multiplied to a dot product, you either take the dot product, then multiply by the scalar, or the scalar goes to one of the vectors, and then you can take the dot product. Okay? But it is not a distributive property because we have multiplication and multiplication. So I'm going to show you a formula that involves the dot product where we can take two vectors and figure out what the angle in between two vectors would be. So we know how to find angles, like the direction angle of any vector. But what if we have two vectors? How do we find the angle in between two vectors? We use this formula right here. I could prove this to you with the law of cosines, but I will not take that time. You're welcome. But no, that's where it comes from, the law of cosines.
Study hall.
Okay. Now, if we have two vectors, technically there would be an infinite number of angles we could measure in between those two. But what this is going to do, it is always going to find the shortest angle. So in this picture that I drew, it would be finding this angle, not the angle that would be more than 180. Okay? You're always going to get an angle between 0 and 180. It's going to be the closest angle distance between the two. Okay? What would our angle be if our vectors were parallel? We have two parallel vectors. What would the angle in between them be? I heard a 0. If I have vectors in the same direction, right, they would be parallel, which means their angle would be 0. Is that the only case? What? 180. If we have two vectors that are going in opposite directions, and their angle is 180, then technically those two would be parallel vectors, right? So you might want to make a note that if our angle is 0 or 180, our vectors are going to be parallel. I believe these are the same two vectors that we had on the previous page. Yes? No? Okay, we're going to find the angle in between these two vectors. Vector v is negative 2i plus 5j. Vector w is 4i plus 1j. And in order to find the angle in between, then the cosine of theta is going to equal the dot product over magnitude times magnitude. So we need to know the dot product and the two magnitudes. Now, we already calculated the dot product together, correct? Was it negative 3?
Yeah.
Okay. Let's talk about the magnitude of v. The magnitude of v. v1 squared plus v2 squared would give us radical 29. 4 plus 25 is 29, right? The magnitude of w, square root of 4 squared plus 1 squared, would be radical 17.
Oh, yep.
16 plus 1.
Yep.
Okay. Glad we're on the same page. So then, using our formula, the cosine of the angle in between would be the dot product over magnitude times magnitude. Now, before you get all calculator happy on me, please remember that if our numerator and or denominator have more than one operation in it, or an operation of any kind, we need parentheses. If you plug in negative 3 divided by radical 29 times radical 17, it's going to do the division and multiplication from left to right. So please make sure you get those in parentheses, otherwise your calculator is going to give you an error. Okay? For this one, for v, we take 2 squared plus 5 squared because those are the components. So we get 4 plus 25. And then for w, our components are 4 and 1. So we take 4 squared and 1. What angle do you get?
97.797.
Hey, I got a pile.
Now, let's plot these vectors. Vector v is the vector negative 2, positive 5. And vector w is the vector 4, 1. Here would be the angle we just found. Does that look? Yeah? Look okay? Yeah. Okay. Just make sure that you get those parentheses in the denominator. You have a product in there. Okay?
She's right on that.
That would not be the description of what you were calling her.
Okay, obviously I know she's not actually correct.
Oh, then don't say it. I don't want to hear it. Okay.
Oh, yes.
We are going to talk about the concept of of two orthogonal vectors. Orthogonal. The heck is orthogonal? Two. It does sound like orthogonal. Two. Well, it has to do with vectors. Okay. Two vectors are orthogonal if they. Well, they're going to share at that point because they're going to be in standard position.
Yeah.
What'd you say?
Said something about like straight.
Okay.
Bones.
No.
First one
No.
Well, some culture got those different orthos.
Oh.
You would want your teeth to look like this, right?
Well.
That one is not a gap.
I ain't trying to look like Michael.
Orthogonal vectors means you have two vectors that are perpendicular. So they have a 90-degree angle in between. Like you want your teeth to be like at a 90-degree angle with your gums, right? That's the goal of braces. Okay. Those of you who are thinking of the orthodontist thing. All right, now let's go back to our if we're perpendicular, our angle is 90 degrees. What is the cosine of 90 degrees?
0.
0. So let's think about this formula. If this right here is 0, and you have the cosine of theta equals 0, that would imply theta is 90 degrees, correct? Well, if this fraction was 0, what specifically about the fraction would need to be 0? If the numerator is 0, the whole fraction is 0. So if our dot product is 0, if our dot product is 0, then u and v are orthogonal vectors. You don't actually have to go through the finding of the angle. Once you get that dot product to be 0, you know that in your formula it's going to be the cosine of theta equals 0, and theta would be 90 degrees. So if your dot product is 0, you're done. You know those two vectors are orthogonal. Write down these two vectors. Vector u is the vector 2, -3. Vector v is the vector 6, 4. So show me your work here. If I ask you anything about vectors being potentially orthogonal, what should go through your mind is the dot product, because if the dot product is 0, you know they're orthogonal. So if we take the dot product, we would take 2 times 6 and add it to -3 times 4. What is that? The dot product is 0, okay? So if I were to ask you, are these vectors orthogonal? You would write yes. The dot product is 0. If I ask you for an explanation, you would need to tell me because the dot product is 0. Okay? I need you to be able to convey that in words. You know that these two are orthogonal because the dot product is 0. Okay. All right, who are my physics peeps? You're in it or have taken it? All right. Please remind me, how do you calculate work? Force times? Yes. Work equals force times, I'm writing distance. Mr. Marsh probably says displacement.
It's still at
What?
You have to write this down.
I would write this down. Okay. Now, what we're going to use to apply to this is that the component of force in the direction of the motion is the only thing that matters. Okay? My son is like 55 pounds. Okay? If I take him and I lift him up 2 feet, I am exerting 2 feet. If I lift him up 2 feet, I'm exerting 110 foot-pounds of work. Okay? Because we take 55 pounds and I lifted him up 2 feet. Now the problem is, what if I put my 55-pound son in a wagon and I'm pulling a wagon at an angle, but he's only moving horizontally? Okay? Well, only the horizontal component of force is actually creating the work because he's only moving horizontally. Okay? And we'll look at a problem like that. So, force times distance, we need to know, but we need to pay attention to the direction in which our object is being moved by the force. Okay? And like real force, not like Star Wars force. Okay? So this is number 72 from 6.4. So if you don't want to like write all of this down, just write number 74 and you can go back and look at those words if you need help or if you're studying. So in number 72, number 72, this is number 72. Well, I'm not assigning it, but in tonight's homework, this is number 72. A tractor is pulling a log 800 meters, and the tension in the cable connecting the tractor and the log is 1,600 kilograms. Those of you who are in physics, I'm really sorry, not everything is measured in newtons. Remember, in math, we often use a different system than what you do in physics. It won't be limited. The direction of the force is 35-degree angle with the horizontal. How much work is being done pulling the log? So, with every good word problem comes a picture. Okay, here's my tractor. And he's driving, well, that was supposed to be horizontal.
He's in Nebraska.
Those poor farmers right now. Okay. Is that better? Okay, so there's the ground. And he has a log that is connected to his tractor with a cable, and it's making a 35-degree angle. The amount of force being used to pull this log is being felt through this cable at 1,600 kilograms. Which way is the tractor driving? Horizontally, 800 meters. So work equals force times distance or displacement, whichever one you want to use. I'm flexible in pre-calc. Well, since the log is moving horizontally, our force is not 1,600 kilograms. Our force is 1,600 kilograms at a 35-degree angle. And since this log is moving horizontally, then I only care about the component of force that is horizontal. So our force is magnitude times the cosine of the angle because we are worried about the horizontal component. this log goes 800 meters. Questions first of all before we get the number. Questions on where we got the numbers.
It's 130.
And we get out of 136.
I got a balance.
Okay, what's our number? 1,000,000. 48,000. 500. 14.62. Now, here's where you're going to get a little uncomfortable, physics people. We took a force of kilograms and we multiplied it by a distance of meters. So we have kilogram meters. If our force was in pounds and our distance was in feet, we would have what we call foot pounds. You just multiply them together. Okay. Questions?
Yeah. Have a good day, Miss Holden.
You too.